Although priority queues can be implemented in a variety of different ways, our focus will be on using the heap data structure, which on average is the most efficient approach. Before we define a heap, let's review the definition of a complete binary tree. A complete binary tree is a binary tree with the following properties. All levels are full except possibly the bottom level. On the bottom level, all leaf nodes are to the left of all missing nodes, if any are missing. What is significant about a complete tree is that there's no missing nodes in a level order enumeration of the tree. We will see that this is an essential feature of a heap. It is sometimes easier to understand the definition seeing a picture of such a tree. On the right is a depiction of the shape of a complete tree. Now that we have reviewed the definition of a complete binary tree, we can define a heap. Incidentally, the term heap is also used to describe the block of memory used in the dynamic allocation of memory, also referred to as the free store. There's no connection with that use of the term and the heap data structure. We begin with the definition of the heap order property for a max heap. The value in every node except the root must be less than or equal to the value in its parent. In a min heap, the requirement would be that there is a greater than or equal to relationship. With these preliminary definitions, we can now define a heap. A heap is a complete binary tree that has the heap order property. It is important to observe that a heap is a partially sorted data structure. Each branch of the tree is in sorted order, yet there's no particular order among nodes on the same level of the tree. A heap can be easily stored in an array using a level order enumeration. For this reason, the actual data structure used to represent a heap is an array, but it will be viewed as containing a tree. To understand the algorithms used in the NQ and DQ operations, it is essential to be familiar with the formulas that express the relative locations of a node with its parent and its two children. In each of these formulas, n represents the array subscript where the value of the node is stored. So if a node is stored at subscript n, its parent is stored at n over 2. The division is integer division that drops any remainder. Also, it applies to all nodes except the root node. The left node, or the left child of a node stored at n, is stored at 2n, and its right child at 2n plus 1. These formulas apply to all nodes except leaf nodes. The root, of course, has no parent, which is why the first formula does not apply to it. There is only one leaf node that can have only a left child. All others have no children. If there is a node with only a left child, it is the rightmost node on the bottom level of the tree. Now let's review the level order enumeration of a binary tree to see how it defines the array subscript where the value of every node will be stored. The numbers below the nodes correspond to the array subscript in which the value of that node is stored. In this illustration, we elected to leave position 0 unused, which is the approach used by the algorithms we will examine shortly. By doing so, no adjustment is needed to our formulas. Next, let's examine how each of the two primary operations are performed, beginning with the NQ, which is the simpler of the two. We have only included the essential part of the NQ method. It accepts the element to NQ in a parameter with that name. In our illustration, the element passed in is 82. Then it checks whether the queue is full. If so, it throws an exception. Otherwise, the code shown is executed. The instance variable length is set to 1 when the queue is empty. So it is a count of the number of elements in the queue plus the empty slot 0, and also points to the next available slot. In our illustration, it is 13 upon entry. So node is set to 13 and length is incremented to become 14. A new node was added in our illustration of the tree. It corresponds to position 13 in the array. Had the value passed in been a small value, we could have put it in that new node. But if we put the element 82 in that new node, we would break the heap order property. So the loop that follows aims to ensure that property is preserved. Then the loop begins. Note the compound while condition. As has so often been the case, the order of the two conditions is critical because checking whether node is greater than 1 prevents accessing element 0 of the array, which we know is unused. The first check is also checking whether we have reached the root of the tree. If not, we compare 56, which is the subscript node over 2, in this case position 6, with what is in the parameter element. Because 56 is less than 82, the loop proceeds. And 56, which is in location 6, is moved to location 13. And node is divided by 2. Without having studied the formulas presented earlier, the meaning of this assignment would likely be hard to comprehend. But we should now realize that this assignment is moving the value to the parent of the previous node. In this case, node becomes 6, which is 13 divided by 2, dropping the remainder. The while condition is still true because node is 6, which is greater than 1, and 71 is less than 82. So 71 in location 3 moves to location 6, and node becomes 3. This time the while condition is false. Although node, which is 3, is still greater than 1, the value at position node over 2, which is 87, is not less than 82, so the loop stops. The value in element 82 is stored in position 3. The heap order property has now been restored. Notice that the path followed was from the newly added leaf back up the branch toward the root. So this loop will execute at most log n times, where n is the number of elements in the queue. One final note is that there's one other important case that needs to be tested. It is when the loop stops because the root has been reached. You can check that case to confirm that this code behaves properly then as well. The dequeue operation is next. Although it is similar, there is one important difference that adds to its complexity. It involves going from the root down a branch towards some leaf node. Unlike the reverse direction, in which there's only one branch to follow, there are many branches in the downward direction. The branch that will be followed we call the maximum branch. Each time when we have to decide whether to go to the left or right child, we will choose the larger of the two. If they happen to be equal, which is possible in a priority queue, we can choose either one. In a max heap, the largest value is always in the root node. So that is the value that the dequeue method must return. We cannot remove that node, however, because the tree will no longer be complete. The only node that can be removed is the one in position 12. So the first step is to decrement length to 12, then save the value in that position, 58, in the local variable value. Next, we save the value in the root node, which is 87, located at subscript 1, in the local variable max value. The contents of max value will be returned on the last line of this method. We initialize node to 2 so that it refers to the left child of the root. The while condition tests whether node is less than length. This condition is a check whether node refers to a node in the tree. Initially, it is true. This if condition is checking whether the left child or the right child contains the larger value. Because there's one node that has a left child but not a right child, we must be sure that that is not the case here. The preliminary condition that checks whether node is less than length minus 1 is there for that purpose. In our case, the root node does have 2 children, and 55 is less than 82, so the right child is larger. So we increment node to point to the right child. Recall that the formula was 2n plus 1. So node now refers to position 3 of the array. Then we compare the contents of value, 58, with what was in position 3, 82. 58 is not greater than or equal to 82, so this condition is false. 82 moves from position 3 to position 1, the root node. Node is doubled to move to the left child, so node is now 6. The while condition is still true. 68 is not less than 25, so the left child is larger. The contents of value 58 is not greater than or equal to 68, so the loop does not exit. So 68 is moved to its parent from position 6 to position 3, and node becomes 12. We have reached the end of the branch, so the while condition is false and the loop stops. 58 is what was saved in value, and it is stored in position 6. And the contents of max value, 87, which was the value in the root, is returned. Again, there's another case that needs to be checked, which is the case when the loop stops because of the break. We would encourage you to check that case to reassure yourself that this method behaves correctly in that case as well. Now let's watch another animation so we can experiment with a variety of cases. So we're going to NQ some values, and the first value I'll pick here will be 60. So I'm intentionally picking a small value to show that when we pick a small value, it can simply be added without moving its way up toward the root. So let me pick one this time a little bit larger. So this time I'm going to pick 90. So 90 will require that it be moved up. Now notice what happened was it moved up this path. What the animation showed was values being swapped, which conceptually is in fact what happens. But in our implementation, we really don't swap them. Instead, what we do is we pull out the one value and then shift things upward. The effect would be the same. All right, so let's do one more, and this time pick a very large value so that it will end up in the root. All right, so 99 is going to be larger than the root. So when it's added, it moves all the way up this branch to the root. And notice what was happening at the bottom. What's at the bottom represents the level order enumeration. And so what was occurring here mirrored what was happening up in the tree at the top. All right, so now let's do some DQs just to get a sense of how that works. So when we DQ, remember that DQ is going to pick the largest value, which is always in the root. So that 99 will go away, but we have to put something in its place. And notice what will happen is what was in the node, the rightmost node on the bottom level, that moved up to the top and then got shifted down the maximum branch. We'll do one more, and this time the 95 will be DQ'd, the 80 will move up to the top, and then some swaps will be needed in order to move it down the right branch. All right, so notice it moves up to the top, then some values get swapped until it's restored to having the heap order property. So that gives you an idea of how the priority queue is implemented with a heap.